Now here the figure shows reversible heat engine, and it is having the heat interaction with three constant temperature system, and we have to calculate the thermal efficiency of this particular heat engine. As shown over here, these are the two sources. T1 is equal to 1000 Kelvin, T2 is equal to 500 Kelvin, and this is the sink where the heat is rejected, and that is T3 is equal to 300 Kelvin. So from these two sources, the heat is supplied as shown by these arrows. So heat is supplied from this source also, and heat is rejected to this particular sink, which is maintained at T3 is equal to 300 Kelvin. The heat supplied Q1 from this source is 100 kJ. The heat supplied is 50 kJ from 500 Kelvin source, and Q3 is the heat rejected. W is the work that is obtained from the reversible heat engine. Now let us see how to find out the efficiency of this reversible heat engine. Now we know that for a reversible heat engine, the cyclic integral of dq upon t is equal to 0. So we can say that q1 upon t1 plus q2 upon t2 minus q3 upon t3 is equal to 0. Q1 and Q2, these are the heat supplied, so they are considered as positive, whereas Q3 is the heat rejected and therefore it is considered as negative. Now substitute the values. So value of Q1 is 100, value of T1 is 1000 Kelvin, Q2 is 50 kJ, this is T2 is 500, and we can easily find out the value of Q3. The value of Q3 that we will obtain is 60 kJ. Now we know that work done by a heat engine is given by heat supplied minus heat rejected. So in this particular case, the heat is supplied from two sources, and that is Q1 plus Q2, and heat rejected is Q3. Substitute the values so that we will get the work done as 90 kJ. We know that the thermal efficiency of a heat engine is given by output divided by input, that is work done divided by heat supplied. Now in this particular case, work done that we have obtained is 90 kJ, and heat is supplied from two sources, that is Q1 plus Q2. So substitute the corresponding values and we'll get the efficiency as 60%. Now let us see another example. Suppose we are having an iron cube which is there at a temperature of 400 degrees centigrade, and it is dropped into an insulated bath containing 10 kg of water which is maintained at 25 degrees centigrade. So temperature of iron bar or iron cube is 400 degrees centigrade converted into Kelvin. Temperature of water is 25 degrees centigrade and converted into Kelvin. So it is 298 Kelvin. The final temperature that is obtained after the steady state is achieved is 50 degrees centigrade. So final temperature is 50 degrees centigrade. So 50 plus 273, that is 323 Kelvin. If the specific heat of water in this particular case is 4186 joule per kg Kelvin, and we have to find out the change in entropy for iron cube and for water. Now as the iron cube is dropped inside the bath containing water, we can say that, and as this is iron cube is at a higher temperature of 400 degrees centigrade, we can say that, so the temperature of the iron cube is 400 degrees centigrade and that of water is 25 degrees centigrade. So naturally heat will be lost by the iron cube and it will be gained by the water. So we can say that mCp delta T for iron cube must be equal to mCp delta T for water. So mCp of iron into change in temperature of iron is equal to mCp of water into delta T of water. Now change in temperature for the iron cube will be temperature of iron cube minus the final temperature. Similarly for water, the change in temperature will be final temperature minus the temperature of water. So we can find out this heat capacity, that is mCp for iron cube as this particular mCp water into Tf minus Tw divided by Tr minus Tf. Now substitute all these values. So mass is 10 kg as that of water. Specific heat of water at constant pressure is given as 4186 joule per kg Kelvin. So it is nothing but 4.186 kilojoule per kg Kelvin. Final temperature is 323. Water temperature is 298. ion cube temperature is 673, and again final steady state temperature is 323. So after substituting these values, we'll get the. Now using all these particular values, we can easily find out what is the change in entropy for ion cube as well as for water. And then if required, we can find out what is the change in entropy of the universe also. So let us see how to find out the change in entropy for ion cube. So we know that for ion cube, the change in entropy will be given by mass into specific heat into log of or ln of Tf divided by Ti. Substitute the values. Just now we have calculated the value of heat capacity of ion, that is 2.99. Final temperature in Kelvin is 323 and ion cube temperature initially is 673. Substituting these values, it will be minus 2.199 kilojoule per kg. Now as the heat is rejected from the ion cube, the change in entropy will be negative. Similarly, we can find out what will be the change in entropy for water. So again, MCP log of Tf upon Tw. Substitute the values. So Tf is 323, temperature of water initially is 298, mass of water is 10 kg and Cp of water is 4.186, and we'll get this value after solving as 3.372 kilojoule per Kelvin. Now as the water is receiving the heat, the entropy of the water will increase. Finally, we can find out the change in entropy of the universe, that is nothing but change in entropy of ion cube plus change in entropy of water. Substitute the corresponding values and you'll get the positive value for this delta universe as 1.173 kilojoule per Kelvin. So we can say that the entropy of the universe is increasing over here. Thank you very much for watching the video. Do subscribe to our channel. Thank you very much.